everybody. First video for 2025. You're not new anymore, but Happy New Year to everybody just the same. We kind of slowed down a little bit with the production of the content because of the passing of our dear friend Omar. But we have to continue same way. So here we go. Little bit of technical knowledge today. As aviators, we need to get a little bit better understanding of our aircraft systems, and today I'd like to discuss the electrical system of our model aircraft and some other things that a lot of people are not as familiar with as they probably should be. We're going to talk about battery voltage and current and how to prepare, how to select the different components for your airplane. Like you have a new plane, what size batteries, the limitation of the various components in the system, so that you don't have a problem and lead to an unsafe situation. Everybody talks about voltage, but a lot of people don't know much about the actual current. So here's a quick example of current versus voltage, right? Now, here's a water tank on top of a tower. You see? The water tank represents your battery. The height of the tower is your voltage. So the higher the tower is above ground, the higher your voltage is, right? Let us say you have an accessory at the bottom like a gear drive. Consider that as your servo or your receiver or your electric motor or whatever the case may be. So once, and this is a switch here, once you open the switch, the current is going to go flowing down the line, right? Anything that causes resistance to the flow is your resistance. The rate of flow is the current, right? So the voltage or the potential difference is the difference in height between the top and the bottom. So the higher the tank is above ground, it's the higher the voltage. That's very basic, right, for your understanding. So now, here is a simple schematic of your electrical system in a basic gasoline powered model airplane, whether 20cc, 30cc, 50cc, whatever. So this is a 2 battery setup. So you have 2 batteries, 2 switches. If you have a regulator on the system, you put it between the switch and the receiver. Here is the receiver. Here are your servos and your ignition BEC and your engine ignition. Right? That's the basic schematic. Now what you have to do is to find out what are the limitations in this system, what is the weakest link here, because that is going to impact the safety of your setup. Right? You need to find out what is the voltage tolerance of each component there, and what is the maximum amperage that each component requires or each component can manage, right? And you are going to make sure you exceed in terms of your current producing capacity and your maximum voltage. Each component must exceed the requirement by at least 25%. What I mean is this now. Let us say you have high voltage servos, right? Each battery, like say a LiPo battery, will have a what you call it now, reference voltage of 7.2 volts. When the battery is charged to the peak, it is going to come up to 8.4 volts. So each component in this system must be able to manage 8.4 volts continuous. If not, you're going to have a problem and something is going to burn out, right? Everybody talk about voltage, and nobody know nothing about current. Now, when you start to get into bigger aircraft and more serious things like jet planes and so, you need to have an idea how much current each component in the system can manage, how much is required, and how much each component can manage, right? Now, what I do for a benchmark is use figures like these. Numbers never lie, right? For a 30cc airplane, each flight will draw approximately 360 amps per flight. 360 milliamps per flight. A 50 to 70cc airplane will draw approximately 420 milliamps per flight. How do I get this? Each servo, for a 30cc airplane, each servo is going to require 50 milliamps per flight. So if you have and also the ignition BEC is considered like a servo. The ignition system is considered like a a digital servo. So you're going to count that as well, right? So like this airplane here now has 1, 2, 3, 4, 5, 6 servos, tracked as well, plus, alright, 5 servos plus ignition makes 6. So 50 times 6 is what? 300. So this should be actually 300. Let us say 300 amps, milliamps per flight, average, right? What you need to do is decide how many flights you're going to do for the day. Normally I do 5 flights per session. So 5 flights with a 30cc airplane will give me 1800 amps. With a 70cc airplane also it will be 2100 amps for 5 flights. If I decide I need enough capacity to do 10 flights, this is a minimum amount of milliamps. 3600 for 30cc, 4200 for 70cc. Now this is your benchmark figure. This figure must represent not more than 75% of your battery capacity. So when you're going to shop for the battery now for this system, you need to exceed these figures by an additional 25%. If you're a 5 flight man for a 30cc plane, you're going to need like say a 2500 milliamp battery as a minimum, right? Or for a 50 to 70cc airplane like a 3000 odd milliamp battery minimum, so you can do 5 flights for the day, right? If you want to push to the 10 flights, you're going to have to either recharge or change the battery or go to a bigger battery that can take everything, and the battery must exceed by whatever this is. You're going to multiply it by 150% basically, or somewhere there, to make sure you have enough capacity so that you have 25% reserve when you finish, right? That is very important, or else you're going to run out of battery capacity. Now the next thing is that not only is this the average amps per flight, but you have a thing called peak amperage. When all servos are stalled and everything is on the load, you're going to get a huge current spike. Every component in the system must be able to absorb that spike without burning out or without getting hot. Now, that means you're going to look for heavy duty equipment, heavy duty wires, 22 gauge wire at least, heavy duty switch, right? High voltage servos that can take 2-cell LiPo, or maybe a lithium ion battery. If you don't believe in so much voltage, you can try a life battery, which has its own limitations. I'm not getting into the battery types today, but the average high voltage switch, heavy duty switch, may be able to tolerate 7 or 8 amps. You can get better ones. The ones I use can tolerate 20 amps each. Let us say one battery decides to fail, or one switch decides to fail. So the remaining switch is going to have to be able to cover everything, or else you're going to lose your plane, right? In a 30cc airplane, mid-maneuver, right, the peak amps will be like 5, 6, 7, 8 amps. So therefore your battery, your switch, your receiver, right, has to be able to tolerate up to at least 8 amps for a 30cc airplane. 50 to 70cc airplane, the peak amps can go up to all 20 amps, right? Usually about 15. A big freestyle pilot can push it up to 20 amps, right? 100cc airplane and up, you're talking even higher figures than this. The switches that I choose to buy are rated at 20 amps continuous each, 30 amp spike. So I make sure that I am well above the bottom line at all times, right? That is very important. So these figures will lead you to choose your equipment, what accessories to buy that are well above the limitations of your entire system. In this case, nothing is going to burn out and nothing is going to get hot under load. I'm going to tell you the main culprit that usually fail now. Many of you might be able to identify what this is, and this is usually the culprit and the weak link in your aircraft electrical system. This is a standard RC connector. See? Usually you have this one coming off of your battery to your switch, or from your switch into your receiver to provide power. Now this boy here is only rated to about 7 or 8 amps maximum. So you see, when you add up everything, if you have one battery and it is going to exceed 7 or 8 amps continuous, this RC connector is going to get hot, it is going to melt and short circuit the thing, and you're going to have white smoke and fire, and your plane is going to crash. So if you know that your system is going to exceed the capability of the RC connector, you need to do something about this. So big plane, from your battery to your switch, you're going to think about a Dean's connector or a XT60 or a JST connector, something more robust that can take, the connector alone can take 20, 30, 40 amps, right? You want a big size receiver now, or probably some kind of power bus to distribute out the current so that you don't have to run through this one, because this one will bring down your plane, see? And then the current will distribute out to everything else. Any one of the components in your plane that cannot manage the current and the voltage, it is going to get hot and it is going to melt, and eventually everything will just stop, right? Good. Your batteries have to be able to deliver the amount of current required, because digital servos will go to full power just trying to hold one single position. And you see, when all of them lock up, you can get a huge current spike, 10, 20, 30 amps. When you get a current spike, you usually get a huge voltage drop. Now, the modern receivers that we have usually will be able to work all the way down to about 3.7 volts. If you get a voltage drop all the way down to that, you're going to go into a thing called brownout, and your receiver is going to go to sleep. And it will lock out, and you're going to momentarily lose control of your plane. And those few moments is enough for you to lose the airplane completely. So when you know that you have a high current demand in your system, you may have to consider 2 batteries, or probably even an auxiliary battery also. 2 batteries come feeding into the one receiver or into the power distribution box, and so the batteries is big enough, and you have 2 batteries now to deliver the current without a significant voltage drop to the system. And that is how you get the electrical system in a significant size airplane to work. Alright, I hope I have made the electrical system quite clear, and I hope you understand the limitations of your system. Again, high voltage system. If you are going to use unregulated LiPo batteries or lithium ion batteries, your servos must be able to be, there must be high voltage servos that can take up to 8.4 volts. Listen, a 6 volt battery has a reference voltage of 6 volts. When it is fully charged, it goes up to about 7.2. A 4.8 volt battery, fully charged, will go up to 5.odd. Right? A 2-cell LiPo battery, its nominal voltage is 7.2 volts, because 3.6 volt per cell. When it is fully charged, it goes up to 8.4 volts. Everything in your system must be able to manage the hot voltage directly off the charger. After the first flight or 2, it comes down off peak a little bit, right? But everything in your system must be able to manage that. Okay? And that is very important. You cannot mix high voltage equipment and low voltage equipment in the same system. You're going to have to use a regulator to protect the weak link, which to me that is nonsense. But you just go all high voltage and just end the argument, right? I think that is all that is there to be said. Remember, you need to exceed, or put it this way, when you choose to buy the battery, the maximum amount of current required for your flight session must not exceed 75% of your battery capacity, and that is a good benchmark when you're deciding what batteries to buy for your airplane. Alright, that is it for now for the basic aircraft electrical system. Now, I am going to reveal some information about our radio control systems that very few, if any of us here in Jamaica, have any understanding about. So I am going to educate you on something now that is very, very important. A word of caution to all of us. Be careful how you mix old and new equipment in your plane. Sometimes they are not compatible and they do not work. Right? Modern radars now have very high resolution, very low latency, and very minute frame rate between data signal waves or pulses, right? And the servos and the receivers nowadays are able to intercept the signal and process it and command the servos what to do, right? The older equipment may not be able to read and interpret the very high resolution modern signals, so we have to be very careful. Now, old Futaba GR system, like say from 20 years ago or 30 years ago, they used to advertise a thing called PCM 1024 technology, right? Pulse code modulation, that is a type of data signal at a resolution of 1024 steps. That means for a servo to travel 180 degrees of swing, it has 1024 steps to go from end to end, of which only 120 degrees of the swing is actually useful. A more modern Futaba or GR or any radar from that era, like 10 to 15 years ago, right, will have a resolution of 2048. That is twice the resolution of 1024. So therefore, within 120 degrees of swing, the servo has up to 2048 command steps to make, of which only 120 degrees is usable, right? Digital servos are able to make use of this high resolution. The old analogs may not be able to interpret this kind of resolution so well, right? And that can be a problem. If you put old analog servos in a modern radar system, the servo will try so hard to maintain, to follow commands and to follow the signal that it burns itself out. It just can't do it. So modern radars are more designed for digital servos and digital high voltage servos as well. We tend to shop for servos based on just the basic specs, how much torque, how much voltage, etc., what kind of servo speed. But that is not enough, because the servos nowadays are so good. The servos themselves can be programmable, not just from a servo programmer, but it can be programmable through a modern transmitter, as well as the servo can be S-bus and F-bus capable, right? An S-bus system, let us think about robotics. Let us think about a robotic arm with 16 servos to perform the same function in unison. All of them will get the same signal through the same wire, right? That wire would be the middle wire in your 3-wire RC connector. All the servos are following the same signal in unison. That's S-bus capable. A modern servo can take a S-bus signal going in or coming out, to the point where you now have to program the servo and tell it which channel to respond to, regardless which servo pin you put it in, right? If the servo is to respond to channel 1, no matter which pin you put it in, if you program the servo to respond to channel 1, that's what it's going to do. And it's not going to work no other way, according to S-bus program. F-bus now is telemetry signal. Modern servers nowadays are so good, they can transmit back to the transmitter peak temperature, maximum current, and peak voltage, right? We never used to hear about them kind of things before. All we think about is the torque and the servo speed and how much voltage it can take. Now when you go and take your money and buy a servo like this, you find say it far exceeds the capability of your old equipment. It may work as well as it may not, we're not even sure. So what we have now, my old GR12X that I bought 14 years ago, it has 2048 resolution, which I explained already. It has has a frame rate or a latency of 22 what's this now, microseconds. That means every 1,000 of every 22 microseconds you get a refresh of the signal that's going out. Right? We thought that was great in those days, but you see now, I mean, the signal to a modern server coming from the receiver, the server takes the signal through the middle, or the white wire or the yellow wire at 330 Hertz, and it is now able to process down to 4 to 9 microseconds. Compare that to 22 microseconds from 14 years ago. Right? So we might have a little problem. The server exceeds the capability of the radio, and the server might have a problem interpreting the signal from the receiver. And if it can't manage it, if they think it is getting corrupt signal because the signal is too damn slow, the server may start to jitter, or it may just go to sleep, or it may just say, look here, I can't deal with this. I might just go to full deflection and just hard over and stop. I think I had that problem with my plane the other day. Right? A modern server has a server refresh rate of 4 to 5 microseconds. So when it is trying to hold signal, if you try to push against it and it's trying to hold signal, it is going to refresh itself. The data is going to refresh itself every 4 to 5 microseconds, while a modern transmitter is transmitting with a latency of 4 to 9 microseconds. Right? So this is an explanation of what happens from transmitter to receiver, down the wire to server. If you're buying new equipment, you must check and make sure everything in your aircraft is compatible. Right? Because I mean, I am an accomplished pilot and I think I fly safely, but guess what? I damaged 2 planes within the space of 1 week, and the problem was like this: the right hand elevator servo in the first plane went to full scale deflection and lock up like that. The airplane was just flipping over like what you call a waterfall now, but the airplane just started going somersaulting like this, over and over. One elevator bent down like this, and there was nothing I could do more than try to pull up, and every time the nose come up, give it a burst of throttle to try and keep the airplane up in the air, until eventually it come down and I managed to flip it over on the back, bada, crash. Minor damage, but I couldn't figure out what was happening. So I come with the next plane now on another day. Another day come, I did a go around, I tried to land, I did a go around. The airplane make a sudden upfloat like this, and I was wondering what is this? When I pushed the airplane over, barely want to come down. I realized one elevator alone was working. So by the time I tried to bring the airplane around the downwind and base leg, one elevator servo working. Every time I pull up or push down to the servo, I'm getting rolled. So the airplane begin to get uncontrollable, and eventually I couldn't hold it anymore and the airplane went down. Both planes damaged. Damage is repairable still, but I'm wondering what happened to my radio system that could have caused this. In both cases, right elevator servo. So the first commonality is the transmitter. I have retired my GR12X transmitter because I no longer trust it. I have more modern servos in both planes, and maybe the signal quality is not good enough for them. So what do I do now? I am now forced to upgrade the entire system. I have to fix the airplanes, I have to replace all of the damaged accessories, props, spinner, landing gear, you name it. I have to go through all of that. I have made a choice of transmitter. Now, the Radio Master transmitter is getting common in Jamaica. That was not my choice. The Radio Master is a very good transmitter, but I think it is more appropriate to those who already have receivers in their airplanes and they want a transmitter that is capable to bind and communicate with different brands of receivers that they have. That is not my concern. My concern is to synchronize everything to the same brand. Everything is modern equipment and everything is the same brand. It should work without an issue. Now, my choice of transmitter is the FR Sky X20 Tandem S. X20S tandem transmitter. It is capable to transmit simultaneously on 2.4 megahertz and 900 megahertz at the same time. And the receiver that I choose is the FrSky TD SR12. Now, the TD is tandem for 2.4 and 900 megahertz at the same time, simultaneously. Right now, this 900 megahertz is strong enough that you can fly a drone through a building and fly it round the backside and come back again and still maintain link. Right? That's why the 900 megahertz is good for long range. The S is a stabilized receiver. It has gyro stabilization built into the receiver. Right? Everybody knows what gyros can do for the airplane also. And that is my choice. I want the strongest link, and I want commonality of from transmitter to receiver to servos, all the same brand, because I can't afford for unexplainable things to happen to me. Right? Everybody else who want to use the Radio Master to cover all the different brands that they have, that is fine. But for now, I am retiring everything and I'm going to straight FrSky. Now, this is a very daunting thing for me because the learning curve can be pretty steep. It is not OpenTX or HTX, it is the Ethos operating system. So I now have to go to the drawing board and sit down and learn all of that, all over. Right? I have to go sit down and learn how to use the transmitter, how the operating system works, and all the different logic that is in the system now. Back to the drawing board, going back to school. But that's what I have to do in order to feel confident in the airplane now. So hopefully by the end of the month or in another 6 weeks I'll be up and running again. But so I have revealed to everybody what has happened to me. Lost both planes in 2 weeks, and I think I have come to the root cause of the problem, which is commonality between old stuff and new stuff. Right? It is time for me to upgrade and to step up now. It might be worthwhile for you guys to think about the same thing. My suggestion to you is, if you have old equipment, stick to old equipment. If you're going to go to new stuff, right across the board new stuff. But be very, very careful how you mix old things and new things, because sometimes they don't work very well together. Alright, that is my lesson for the day, and I will see you again soon with another video. Feel free to make comments as necessary. We have a group chat, and maybe one day these videos might get to YouTube as well. Alright, enjoy the rest of the day and safe and happy flying.